here is my part one for the temperature versus time mass flow. So right here is the system, and Fn is the flow rate going into the system. Tn is the temperature of the particles going into the system. The Ti is the temperature in the system. H is the height of the water. The area is A, the area of the system, like the cross-sectional. And F out, we get equals alpha times height to the 1/2, or to the half. So square root of H. And multiply that by the temperature coming out of the system. A little background. We'll say E equals enthalpy, and A alpha is 0.4. A is going to be referred to as area. Alpha is going to be referred to as alpha. So let's get started. Okay. So what we're going to do is start putting together equations. So we'll get, alrighty, so for our first equation, what I'm going to do is going to do the mass of the system sometimes you have to get slow with this, equals the mass going in minus the mass going out. Alrighty, so now what we're going to do is base all of our equations off of this. So we'll say dt is the time it takes. And there we go. Alrighty, now what we'll do is do d density times the area times height divided by dt equals density times flow rate in subtracting density times alpha h to the half. That looks pretty good. Alrighty. Now, after this, what we're going to do is cancel out the densities because they can cancel out there. And let me reword this here. So A equals dH of dt. And we could honestly move the A over to that side. So dH over dt equals Fin minus alpha h to the 1/2 over area. Alrighty. Now let me jump real quick to the energy equations. So that's going to be kind of like our starting point right there. Now let's jump to the energy equations. So let me circle this because we'll come back to that. Alrighty, so what we'll do, I'm sorry I'm looking down. I'm writing down on the iPad here so that it goes up to the screen. Alrighty. So, I do not know what is happening. I will be right back. Alrighty, so now let's jump to the energy systems equations. So we'll get the amount of energy times U plus plus kinetic energy plus potential energy. And that equals enthalpy plus kinetic plus potential. That's N multiplied by the mass going in. So let's simplify that a little bit. So we'll get the mass of the system equals enthalpy N mass N minus enthalpy L times the d m going out over dt. Alrighty, so now let's combine those two equations here. So we'll get dH, yep, let's combine them. So we'll get D density times the area times the height times the system over dt. And then for the right hand side of that, we'll get enthalpy N times the density of the flow initial minus enthalpy out and then we'll go all of that times density times alpha times h square root. Alrighty, now what we do, since this is kind of a cluster, let us, hopefully you could see that, let us kind of simplify all of this together. So we'll get dH and then the U system times T equals enthalpy N times flow rate N minus enthalpy out times alpha h to the half, because all the densities canceled out and we could move some over. We can move the height over, or sorry, not the height, the area. Could get the area out. Alrighty, now what we will do is do the chain rule. No, we will still continue to simplify the derivative. So dH CP. This is going to be the U system that we saw for earlier. Temperature minus the temperature reference. The reference is negligible, so we'll end up canceling that out anyways. Times the area. All divided by dt equals, hopefully I'll be able to fit this in, TP times the flow rate initial minus, work for me, minus, and I'm going to put this part down here because it will be kind of like that, T minus T ref times alpha H to the half. Alrighty, let me see that. Hopefully the reflection isn't blocking it. Now what we'll do, cancel out all of the CPs and the T refs. So we'll end up getting dH times T times the area dt equals T times Fn flow rate N times temperature alpha height to the half. Alrighty. Yes, those look like J's, but they're T's. So let's do even more. Let's do the chain rule now. So we'll get H dt over dt plus T dH over dt. Then work equals T times flow rate N minus T times alpha H to the half divided by the area minus, this will go over there, T dH over dt, and then the height will also go over here, over H. So we end up getting dt over dt equals T times F of N minus T times alpha H to the half divided by area minus this differential equation dH over dt parentheses all divided by H. And now what we're going to do is we're going to code this and compare the graphs that we're given. Alrighty, so this will be the coding part of mixing dynamics, and this will be the temperature, not the concentration. So right now, let me just update. So we have the import, we're getting everything set up, making sure that we have the plot set up, and I edited it so that the graph or chart will be black instead of white. That way it's a little easier on the eyes. I listed all the variables here. So we have time is at 100 seconds, area 1 meter squared. This will be the temperature in kelvins, and that's the initial temperature there. At 300, the height is 1 meter. And then let's see here, that temperature so this is temperature into the tank, and that's at 320 kelvins. This is the flow rate into the tank, and that's 1 meter cubed per second. And then the alpha is 0.4, and that's the flow rate out of the tank. So I'll just run these just to get them started. There we go. And now we could start coding. So now we gotta define the right hand side of this equation. T, K, those are two good variables. T will be time, and K will be constant. Then what we'll do is we'll do AB equals K. And we'll set up the first equation. Flow rate in. This is from the previous section, so this is just writing down the equations into code. Minus alpha, I think is what I called it. Then let's see, alpha times area, call it area, and that's to the square root, or not to the square root, to the 1/2. So it is the square root, but it's not to the square root. Then divide that by the area. Wait, sorry, that is not the area. That is going to be this new, that variable. dB equals, there's going to be a lot of parentheses in this one, so I'll get that out of the way. I might need to go back and do more. En minus, times Fn, flow rate in, sorry for the tongue clicking and do that. Then we'll do minus A minus B times alpha times A to the 1/2. Alrighty. And there's gonna be divided by area, and then minus B times dA divided by A, but we need one last parenthesis, so there, make sure it fits. There we go. Alrighty, so that's our two equations set up, and we have an array from them. Now what we're going to do is we're going to return it, numpy array, and then we'll call it dA, dB. There we go. Let's run that, make sure we don't get any errors, and let's add some more code. So now what we will do is do the equation, or set up the equation. That's a setup. Now we're starting to solve it and get the plots for it, the plot points. Solve underscore IVP. Because it's the time interval. Numpy array. array by the height, and then temperature. The method is Rado. And we will do dense underscore output equals true. So that will only give us the true dimensions of the plot. And then dot solution. Solution. There we go. Alrighty, now let's name it tplot because it's temperature equals numpy dot linspace, setting up all the points and intervals, time, comma, 300. Bang. AB equals EQN, and there is our plot. But we still need to do the figure and subplot. So there we go. Let's run that. Let me run through it here. HITI. What is invalid syntax? It might be because there's a space. No. Rado. Oh, sorry. Method equals Rado. No? Name plot is not. Oh, that would be my bad. Tplot, not just plot. Tplot time should work. There we go, guys. Nice. Alrighty, now let's set up the figures. We will go fig. Oh my lord. Fig equals make subplots. We'll do rows equals 1. Sorry. Columns 2. We'll call it fig.add scatter x equals the plot, comma, y equals a, comma, row equals 1, and column 2 equals 2. Tplot just like the last one, except this will be y equals b, row equals 1, column equals 2. Oh, sorry. Column equals 1 for this one. That way they're on 2 separate things, and it gives us 2 plots. Should be it. Alrighty, here are the 2 plots. They look really nice. I'll get back to you. We need to do the second part, which is going to be mixing dynamics with the concentration there instead of temperature. Thank you. Okay, so now what we're going to do is we're going to create an equation for the concentration instead of the temperature. So we have the same exact setup. We have height, we have the flow in, and we have the area. The only difference is we have the C in the concentration in the tank or the system, and we have the concentration going in, and that will also change the flow rate. So as you could see here, we have flow out equals alpha H to the half times C out. Alrighty, let's get started. This is our equation from up there. This one right here. Yeah, let's get started. So we know that the density of the system will stay the same throughout. So density of system equals density in equals density out. Alrighty. Now we also know that the concentration out is going to be the same as the concentration of the system. Although the scale might be less, the proportion will be the same. So let's just keep that in mind. Alrighty, so what we're going to do is use the equation from the first one. The mass of the system equals the mass in minus the mass out at a given point. So what we will do is write that out. dm of the system over dt equals dm going in over dt minus the dm going out over the dt. Then from there, we basically do the same exact thing that we did before. We could kind of skip because we already did we already know where the variables go. And so what I'm going to do now is write out this equation. dc times the area times the area times the height divided by dt, and that would be the system's mass, equals the concentration going in times the flow rate, and that will equal the mass for that equate for the dmin out or in, sorry. The mass in equals concentration in times flow rate, and then we'll subtract that by the mass going out. So that will be C times alpha H for 1/2. Then what we could do is start to simplify. So we could bring the area over to that side, over to the right hand side, and make sure that we have the right hand side equation so that it's easier to graph. So we'll also need to do the chain rule here. HDC plus CDH over dt equals concentration going in times the flow rate going in minus concentration going out times the alpha height square root. All that divided by the area. And then what we do is we move the HDC over dt over to the other side, we move the CDH dt over to the other side, and we divide the h. So we end up getting, for our final equation that we're going to graph, dc over dt equals Cn minus flow rate in minus concentration alpha times h, and then the square root of that, all divided by the area, then subtracted by c dh over dt, and then all of that times the h. Sorry, I mixed up the variable here. This should be d little h, and then little h there. Sorry for the confusion. So that is what we get. We get dc over dt equals concentration going in minus the flow rate going in. Sorry, times the flow rate going in. My bad. Minus concentration times alpha times height, and the height is the square root, divided by the area, and then all of that subtract concentration of dH over dt, and then all of that multiplied by 1 over h. And that will hopefully give us a graph. I'll see you when I start to code the concentration. Alrighty, welcome back. Here's going to be the concentration part of mixing dynamics. Yep, here we go. So as you can see, had the same start, same setup. Then for our time, area, height, flow rate in, and alpha, it's all going to be the same. So the only change is going to be, instead of temperature initial and temperature in, we have concentration initial and concentration in. Now, since we figured out through the derivatives and differential equation that this equation is the same as the concentration equation, basically we could do some easy work by copying and pasting into here and then changing the variables to what it should be. So I'm going to do that real quick. Need another code. There we go. So we're going to change basically every t to a c. C, and it's still going to be plotted against time, so we don't need to change the time interval at all. And let me run it. Oh, I forgot one. See if it works, and that is going to be our graph. So as you can see, it reaches a kind of limit at 1. And let's go slightly above 6. It's going to be the same thing for this, except for the second graph, it will be a limit of 320. So yeah, thank you very much for watching.